All right, so in this topic, we're going to be talking about free body diagrams. Not so much how to solve a particular problem which uses them, but what to be aware of when doing free body diagrams and how to approach them. So first of all, keep in mind that you always have X and Y components. So generally, when you do a free body diagram, you're going to have whatever it is that you're doing the diagram for, and you're going to align some X and Y axes. And so usually, the y-axis will be up like this, up and down, and the x-axis will be left-right. Usually. So the other thing to keep in mind is that, say the thing you're doing a free body diagram has a force that's like going in this direction, and then, I don't know, a force going in this direction. Let's just call these F1 and F2. Two things to keep in mind here. First of all, you do need to know your trigonometry, because notice that this one here is not aligned on either of the axes. It's off at an angle here. Call it angle theta. And what's important about that is you need to be able to decompose this vector into two component vectors. So you would have F1y, and you would have F2x. And the reason you need to do that is you have to keep in mind that the purpose of the free body diagram is that you're going to get over to doing a summation of forces. And if I'm adding things together, remember vectors have x, y, and sometimes z components, and they're pointed in different directions. It doesn't make any sense to add something pointed in a y direction to something pointed in an x direction. You can't do that. You have to add only x components, only y components, and if you had it, only z components. So when we get to sum of forces for something like this, say I did the sum of forces in the y, it's important that I only do y forces. And if we decide this is the positive direction, again, that is usually up to you. You just have to be consistent with how you label things. And keep that in mind that you could just make this positive and this negative. Everything would still work out algebraically. So don't get too hung up on the free body diagrams as well. If you ever have something that's sort of tilted a bit and you have to move everything around, get comfortable with that and learn to just decide which direction is going to be positive and negative for you. But if I make this positive and negative in the usual sense, anything pointing up would be positive, and then I would subtract anything pointing down. I'm not going to say what that's equal to yet. And then for sum of forces in the x direction, well, you would only do things in the x direction. Notice before I decompose this, I didn't have anything pointed in the x direction solely, like I had something pointed in the y direction here. But when I decompose this vector that's at an angle, some portion of that points in the x direction. And it's pointing in the positive direction, so it will be positive. So I'll just put F2x. Now, it's important to remember too that just like it's arbitrary which directions I call positive or negative for my axes here, if I can figure out which way to point my fingers and pinky to get different positive directions, you could be given something like north, south, east, west as well. And you would be expected to set that up. So this would be north, south, east, and west. And you have to set that up and use everything in those terms. And you might see terminology like 45 degrees south of west. You might see something like that. And if you saw something like that, the way you would interpret that is west is over here. So starting at west, I go 45 degrees south of that. And so this would be 45 degrees south of west. So keep that in mind as well. Now, the other thing to keep in mind is that when you do your free body diagrams, it is important to actually refer back to what's physically going on in the problem. Because suppose that this was a car on a road. Well, I suppose that wouldn't make too much sense for the vector pointing that way, would it? So let's assume it's a box on a table, and I'm pulling on it with a rope like this. Well, the thing is that unless the box is sinking into the table or floating up off of it, it's not moving. If something's on the table, even if it moves this way, in the up and down, in the vertical direction, it's not moving. So when I do my sum of forces, I have to remember that I know from the context of the problem that altogether these should equal, in this case, 0. Because if it didn't equal 0, what that would mean is that this thing is moving up or it's moving down. It has some movement or an acceleration in either direction. The other thing to keep in mind is if it is moving, so if I'm pulling a box with a rope and it's just moving this way, then I know that it's not equal to 0. There is some total net force, and therefore there's an acceleration. And so in this case, it would be the mass of whatever this thing is times that acceleration. And so free body diagrams are incredibly important because they let you get from here to here. And once you get here to your sum of forces, then you can start doing math. Then you can use algebra. Then you can solve for things, right? And then we all know what's going on. But to visualize all of this, what's going on, especially if you had like 7 forces here, you need to be proficient with the free body diagrams and be very careful about how you label them. Make sure you use your trig to decompose the vectors and solve. Make sure to understand north, south, east, west type of notation. And again, remember that if something is not literally moving in a direction, then that sum of forces is set equal to 0. Otherwise, it's always set equal to the total mass times the acceleration. And that was a topic in discussion on free body diagrams.